So in the last lecture, we have looked at the equilibrium equation in the spatial form. And if you remember, this equation followed from the balance of linear momentum in the deformed configuration. We localized this form and we said that the accelerations at every point are negligible, so we put the right hand side equal to 0 and led to this equation, which also can be written as divergence of sigma plus b equal to 0. So for every equation that we derive in the spatial form, there's also, just like in case of the mass balance, there's also a material form of the same equation. Now, this is the reference configuration and this is the current configuration of a body, and I have chopped out the upper part of it. So the upper part has not been drawn. On the deformed configuration, the traction transmitted through the small yellow area d small s is T, and therefore the net force that is transmitted through this yellow area is, let's say, dF equal to T ds. Now this is called the true traction because dF is the true force that the upper part of the body exerts on the lower part. So if I want to calculate the total force that is transmitted by the upper part to the lower part through this surface S, I will have to integrate dF over S. Now, so this will be equal to T ds, that will be equal to sigma n ds, where sigma is the Cauchy stress. Now, d capital S is the corresponding area from which d small s is mapped, and it has an outward normal equal to capital N. What is the traction that I would have on this small area? Whatever this traction may be, by Cauchy principle, I must be able to connect the traction to the normal through a stress-like quantity. Therefore, I should be able to write, if the traction I say is T1, I should be able to write it is equal to n times some quantity P, where P is a stress-like quantity. Now, we have to realize that this traction, the definition of this traction, is not unique. For example, the total force transmitted in the true configuration of in the current configuration of the body, as we have mentioned, is this. And now I can say that the total force transmitted through this small area is equal to this force at each and every point on this boundary, and therefore this is equal to dF naught integrated over S naught. But I can say dF naught 1 integrated over S naught. I can equally say that over S naught I will get dF by integrating, let's say, F times dF naught, some other dF naught 2. So for each of these definitions which I make up, I will get a different measure P, different measure of stress in this configuration. So that is what we are now going to show for two possible cases, two important cases that we are going to encounter. In the first case, we are going to say, we are going to make this statement, and we are going to say that the traction, the force transmitted through this is point to point equal to the force transmitted through this. Therefore, if the force transmitted through this is T1 times d capital S, this is equal to dF naught, and this dF naught is point to point equal to dF. So obviously, if I integrate this dF naught over S naught and this dF over S, I get the same result. So This is my first assumption, and this will lead to a measure of stress that we are going to work out now. This traction, which comes from the definition that point to point the force transmitted in the two configurations are equal, this traction is called the nominal traction. Remember, the traction has to be related to a stress-like quantity through the normal. So this follows from Newton's third law, and therefore this always must be valid. So now, once we have this basic definition by which the tractions in the current and current and reference configurations are connected, we will have to find the stress-like quantity that corresponds to the defined traction. Now, let us do this for the nominal traction. Now, we assume that for the nominal traction, the stress kind measure connected to the nominal traction is this fancy P, which is called the nominal stress. And therefore, T1 ds is equal to NP ds, which is what follows from the Cauchy principle now applied to the reference configuration. And we have already made the assumption that point to point df is equal to df naught 1. df naught 1 is T1 ds, and df is T ds, small t ds. Small t is n sigma ds. T1 is np ds. We still don't know what this p is, but we are going to find out from this definition. And then, because sigma is symmetric, n sigma can be written as sigma n. Np can be written as p transpose m. That's easy to see. N times another second order tensor. The ith component of that is nk p ki, which can also be written as pki times nk, which when converted to vector form would be p transpose n. So it can be np can be written as p transpose n. That's what we have done here. And then we use the Nansen's relation for n ds. We replace it by j f minus transpose capital N ds, and here we have fancy p transpose n ds. We have n ds on both sides, so it immediately follows that p transpose is equal to j sigma f minus transpose. So this is the relation, this is the new stress that we have defined. Obviously we can take transpose of this and write p is equal to j f inverse sigma transpose, which is equal to sigma. So this is the relationship between the nominal stress and the Cauchy stress. So I have defined a new stress measure starting from the assumption that df is equal to df naught, so that point to point I am transferring the same amount of force. Our tractions are such that point to point I'm transferring the same amount of force. Now, most of the time, the transpose of the nominal stress is given a name. So P transpose, which is transpose of the nominal stress, is sometimes called P, which is the first pk stress, first Piola Kirchoff stress. And from here, it's easy to see that fancy P transpose is equal to PJF minus transpose. So this is the relationship between the first Piola Kirchoff stress and the Cauchy stress. When you use the first Piola Kirchoff stress, remember that T1 ds was n p ds. So this is the nominal stress. This can be written as P transpose n ds, which is equal to P n ds. So the traction for the first pk stress is P n ds, and for the for the nominal stress, it's NPDS. So that's the difference between the two. Most of the time we will use first PK stress, not the nominal stress, but this is to remember. Now sigma is symmetric, so P need not be symmetric because F is not necessarily symmetric, but P F transpose is symmetric because sigma is symmetric, P F transpose is symmetric. Now let us go back to our principle of balance of linear momentum. So the expression that we had started with in the last lecture was this. So rate of change of the total linear momentum is equal to the force applied due to surface tractions and due to body forces. We can change this dv to d capital V. J dv is the trick, and then this domain of integration changes to omega naught. Here also we do the same thing. J dv replaces the small dv, and this becomes omega naught. Bj is the body force vector in the reference configuration, so we can give it a different name. We can call it B naught. So we have B naught d capital V. Here we have rho naught V d capital V, ddt of that. You can take the ddt inside because rho naught is not a function of time, and neither is this one. This term needs to be now handled. So this is how we are going to do it. So the term is TdS, integrated over d omega, and we will write T as n sigma, which can also be written as sigma n because sigma is symmetric. And then nds will be replaced by jf minus transpose capital nds, d capital S, and the domain of integral will change from d omega to d omega naught. So once you have done this, go back and look at the relationship between sigma and P. So we can get it from here. 1 by J P F transpose is equal to sigma. So go back and replace this by 1 by J P F transpose, and then you have J F minus transpose capital N D capital S. So the J and J cancels, F transpose and F transpose minus gives you identity, and you end up having TdS integrated over the deformed surface equal to Pn integrated over the undeformed surface. So obviously you can apply divergence theorem to this, and you will get a volume integral which will be over the deformed over the reference volume. If you want to do it in initial notation, this is how you will do it. So this Pn is Pik nk d capital S, and applying divergence theorem to it, convert it to del Pik del capital Xk dv. So now we take this back to the term here. So this is so everything is over omega naught and d capital V. Therefore, we can now apply the localization theorem in exactly the same way as we had done in case of the spatial coordinates, and this is the equilibrium equation that we will end up with. The equilibrium equation looks exactly like what it looked for sigma, except that here you have the first pk stress, and here you have the body force referred to in the reference configuration. Remember, B naught is equal to J times B. So this is your equilibrium equation in the reference configuration or in the material form. Now let us try something slightly different. Now, as I had mentioned before, the total force that the upper part of the body exerts on the lower part through the surface S in the deformed configuration is integral over S d small f, which is same as T ds integrated over S. Now, we had earlier assumed that df and df naught are point to point the same. Now let us say that we have another df naught which is f, so that f df naught is equal to df. So the total force that is transmitted by the upper part on the lower part is of course this, and then it is obtained in the reference configuration by doing this. So I can do this, and there are some advantages of doing it. So now I am assuming that df, f inverse df is equal to df naught. I call this df naught 2 just to distinguish it from this df naught. So f inverse df is equal to df naught, which is actually analogous to f inverse d small x equal to d capital X. So the elemental force transforms in the same way as the elemental line element does, right? So this is just a synthetic thing to do, but this will lead to another stress measure called the second Piola Kirchoff stress. And always remember that that will lead to a traction which will be related to this new stress measure, which we will denote by S. So this has to be always valid. This kind of a relation between the stress, the normal, and the traction always has to be valid because it's mandated by the Newton's third law. Uh, but the way I get this integrated force from the elemental forces in the reference configuration is a choice that I make, and in this case this is the choice that I'm going to make, which means that this is the choice that I have made. Now once you make these choice, you can end up with a new stress measure S, which we call the second PK stress. And the second PK stress has some advantages. The first advantage is that the second PK stress is symmetric. Unlike the first PK stress, it's still defined in the reference configuration, but the second PK stress is symmetric, and it's related to sigma and P through these relations. Now, if you use these relations, you can actually show that df naught is now f inverse df. How do we do that? So let's start with df. df is equal to t times ds. This is the true traction. T is sigma times n ds. It's n sigma ds, but sigma is symmetric, so sigma n ds. And then in place of sigma, let us use this. So we know that sigma is equal to 1 by j f S F transpose. This is our definition of the second PK stress. We have done that. And then in place of NDS, use the Nansen's relation. So F transpose F minus transpose cancels out, and you are left with FSNDS. FSNDS is what you are left with. This part is, of course, this whole part is, of course, your df naught, which we will call df naught 2 to distinguish it from the first PK stress, from the force transmitted by the first PK stress. And now to get df, I have to do f df naught 2. Whatever you get from the stresses, that means whatever you get by multiplying the stress with the normal and then the elemental area, you have to multiply it by f so that you get the true force that is transmitted by the upper part to the lower part. Now, and here I have put together a handy table that gives you the relations between sigma, P and S. I have also added a new stress, tau, which we will use much later, but it's called the Kirchoff stress, which is simply J times sigma, and its relations with the first and second PK stresses are given here. This is a handy table that we will have to use in order to manipulate equations in finite elements. Now let us do a small problem. Here's a motion. It's a rigid body motion. There's a body that's spinning about some axis at an angular velocity omega, and we are interested in evaluating the pk1 and pk2 stresses at t equal to pi by 2 omega. At t equal to pi by 2 omega, this is 0, this is 1, therefore it's minus 1, this is 1, and this is again 0. So you have you have a q, you have a motion given by x equal to minus capital X and y equal to uh, x equal to minus capital Y and y equal to capital X. Therefore, your deformation gradient is 0, del x del y is minus 1, del y del x is 1, and this is 0. So this is your deformation gradient tensor. Now, once you have the deformation gradient tensor, we also have the fact that while the body is rotating, the stress acting on it, which is like sigma x naught in the x direction and sigma y naught in the y direction at time t equal to 0. This is the state of stress at time t equal to 0. This stress state remains fixed to the body and rotates with it. So at time t equal to pi by 2 omega, the body goes into a rotation by 90 degrees, so that this sigma x naught comes here and sigma y naught goes here. So this is at t equal to pi by 2 omega. This is the deformed configuration. Now, in this state, the Cauchy stress is sigma y naught in the x direction, sigma x naught in the y direction. So this is the Cauchy stress at time t equal to f is this, and j, of course, the Jacobian of this is equal to 1. So j is equal to 1. Now once we have this sigma f and j, we can calculate f inverse, we can calculate f inverse transpose, and we can calculate the first Piola Kirchoff stress. So this is the first pk stress. This is what it comes out to be. This is just the mathematical manipulation, and we can do s as well once we know f inverse and f inverse transpose. So this is how we do s, and this is what it comes out to after the mathematical manipulations. Now let us try to understand, especially try to understand why p is shaped like this. Do that, look at this picture. So this is the reference configuration, this is the deformed configuration after a 90-degree rotation. So after a 90-degree rotation, this surface, let's say its area is d capital S, it rotates to this blue surface. It rotates to this blue surface. And then what is the force transmitted through this red surface? It is the force transmitted through it is P capital N D capital S, and that will turn out to be minus sigma naught. So P in this case is P is 0 minus sigma y naught, sigma x naught 0, and then for this surface, the normal is E2, the normal is E2, and you multiply it with n is 0 1, so this leads to n d capital S. So this leads to the force that is transmitted through that surface, and that is equal to minus sigma y naught 0. So this is the force, this is the force that is transmitted through that red surface in this configuration. Now what is this red surface comes to this blue surface after the rotation in the deformed configuration. After rotation through this deformation gradient tensor, it comes to this blue surface, and then what is the force transmitted through this blue surface? The force transmitted through this blue surface is sigma times n, but this n is now minus E1. So your sigma in this state is sigma y naught 0 0 sigma x naught multiplied by n, which is now minus 1 0, times d small s will give you again minus sigma y naught and 0 times d small s. D small s and d capital S are the same, so this is d capital S, which shows that the force transmitted through the undeformed surface is the same as the force transmitted through the deformed surface, which is this. So that is why to ensure this, your P has this particular form. Now, the other problem that I wanted to do was this one. So we have a square bar, cubic bar, cuboidal bar, which has dimensions A naught, L naught, V naught, and it is stretched in one direction, let's say the Z direction, um, or the X direction, this is the X direction, to a new length L, so that its cross sections diminish to new dimensions A and B. This is the motion, and the F is easy to calculate, and the F is diagonal in this case. It is L by L naught, A by A naught, and B by B naught. Now, if I am doing this with a uniaxial stress, my Cauchy stress tensor is just sigma x 0 0 all over, and I will calculate the first pk stress for this situation. To do that, I have the F, I'll have to calculate F inverse, I have to calculate determinant of F. The Cauchy stress is this, and then I will use the formula simply to calculate my P, which turns out to be AB sigma x by A naught B naught. So this is your P11, and the P11 turns out to be A times sigma x divided by A naught, where A is the current cross-sectional area of this, by A naught, which is the original cross-sectional area in the reference configuration. So this is A naught and this is A. So what the first pk stress gives, this is the true force that is transmitted through the current cross section divided by the original area in the reference configuration, gives you P11. So from this example, you see that P11 is like the engineering stress, which is always divided by the original area, whereas sigma is more like your true stress. S can also be calculated, but it is difficult to ascribe a physical significance to S. So here is our last problem on this section. So this is a motion. It's difficult to see right away what kind of a motion is it, but this is the Cauchy stress that acts in the deformed configuration, and we have to calculate the first pk stress, which is pretty simple in this case, if we use the straightforward mathematical procedure. So the straightforward mathematical procedure would obviously involve finding F inverse, and then P j equal to J sigma F inverse transpose will give you this pk stress, first pk stress. Now, this first, let us now use the Nansen's relation. So let us assume that in the deformed configuration, we have a surface with n equal to E2. Okay, in that case, F transpose n is 0 minus 6 0 half 0 0 0 0 1/3 times n, which is in this case 0 1 0, which leads to half 0 0. So F transpose n is half 0 0 d small s, and J for this is determinant of F is 1. You can verify that determinant of F is 1, so J doesn't count. So uh, this is what capital N D capital S is. You can write this as capital N d capital S as uh, half E1 times d small s, which means that a surface which has a current normal of E2 came from a surface whose normal was in the E1 direction, and it had half the area as in the deformed configuration. Now, uh, this is shown in the next slide. So this is your reference configuration. This surface with the cross has gone to this surface with the cross, and sigma 22 is acting in this direction. Sigma 22 is acting in this direction, and the traction on this surface in the deformed configuration is sigma 22 n, which is equal to sigma times n, which is 0, 50, 0 times n is in the two directions, so 0, 1, 0. So the traction is 0, 50, 0. And since the force transmitted through this surface will have to be the same as the force transmitted through this surface, then the force transmit the and the areas we know of a surface that has a current normal in the E2 direction, it came from a surface which had its normal in the E1 direction, that means on this surface, then the traction on this surface has to be 0, 100, 0, because the area of this surface was half of the area that it currently has. Okay, so that completes all the problems that I wanted to do. There's assignment, there's a set of practice problems that I'm going to upload now, and that should be available in hello.iitk.